Okay, so the other kind of improper integrals that we're going to be looking at are integrands with vertical asymptotes. You can kind of think of the last examples that we were looking at as ones with horizontal asymptotes. Okay, so just a couple of definitions again. If f of x is continuous on the interval not a, but all the way to b, and discontinuous at a, then if you try to integrate from a to b of f of x dx, right, the problem here is that my lower limit is discontinuous on my function. It turns out that you can still do this by again doing a limit. So we're going to take the limit as c approaches a from the right of the integral c to b f of x dx. All right, same kind of deal, but the other way around. This time, let's look at having the integral from a, including a, up to b, and it's discontinuous at b. Then if we integrate from a to b, now my upper limit is discontinuous, so I'm still going to do that limit, but now as c approaches b from the left, then from a to c, f of x dx. Sometimes you're going to have it continuous on the interval a to b, including a and b, but discontinuous at c, which is somewhere in between a and b. Then, if you try integrating from a to b f of x dx, somewhere in my interval from a to b, I have a discontinuity. What you have to do then is combine steps 1 and 2 together, integrate from a until you get to that discontinuity, plus integrating from c until b. Again, doing the limits like you did from up above. Okay, so let's look at some examples. One thing I will say is that I am not going to tell you whether something is an improper integral. You need to be able to recognize them. So if we're looking at the integral from 0 to 1 of 1 over 1 minus x dx, if this was a test question, again, I wouldn't say there's a discontinuity. You would have to notice that if I plugged 1 into the denominator, it creates a vertical asymptote, which means that my upper limit 1 is discontinuous there. So discontinuous at 1. Because my upper limit is discontinuous, we're going to rewrite this as a limit. We're going to do the limit as c approaches that 1 from the left. The reason we're approaching it from the left is that because that's the upper limit, I'm going from 0 to 1, so I'm approaching 1 from the left. Of the integral from 0 to c, 1 over 1 minus x dx. All right, so a quick little u substitution here. We'll let u be 1 minus x, which means that du is going to be negative dx, which means I'm going to have to divide that negative sign over. So still the limit as c approaches 1 from the left, but now it's the integral. Because we're changing over to u's, my limits have changed. Now it's going to be negative du over u. That has antiderivative. If I bring the negative sign out, 1 over u has antiderivative of natural log. So still the limit as c approaches 1 to the left of, go away network settings, nobody wants you. Of negative natural log of the absolute value of u, which is 1 minus x. This going from 0 to c. Okay, if I plug c into there, still the limit, c approaches 1 from the left of negative natural log of c minus x. That's going to be then plus the natural log of plugging 0 in for the x, which is the natural log of 1, which is just 0. Okay, now let's worry about the limit stuff. Oh, I plugged the c into the wrong spot. Sorry about that. I don't know what I was thinking here. I should have been plugging the c in for the x, so this is 1 minus c. Okay, let's look at plugging 1 in and having it approach from the left. If I just try plugging 1 into this, I get the natural log of 0, and the natural log of 0 is undefined. So let's look at what happens to the natural log graph as I get closer and closer and closer to 0. Well, we can just do that in the calculator. So let's look at the natural log as I keep getting closer to 0. Natural log of maybe 0.2 is some crazy number. Natural log of 0.1, a little bit bigger of a negative number. Natural log of 0.000001, even bigger. And this is just going to keep getting bigger and keep getting bigger and keep getting bigger. So in other words, if I try to plug 1 in for this c as it approaches from the left, this is just going to blow up to negative infinity. But it already has a negative sign out in front, so it goes to positive infinity. What that means is that this particular integral diverges. This integral. So this does not have an answer to it. There's no area that satisfies that. Okay, let's look at one that would, though. Let's do the integral from 0 to 3 dx over x minus 1 to the 2/3. Okay, so this also has a discontinuity. This one is discontinuous at 1. 1 is in between my limits. What that means is that we're going to have to split this up, having the integral from 0 to 1 of dx over x minus 1 to the 2/3, plus the integral from 1 to 3 dx over x minus 1 to the 2/3. And then for both of these, we're going to have to do that limit. So we're going to do the limit as b approaches 1 from the left for this first integral, integral 0 to b dx over x minus 1 to the 2/3. Plus here, the limit as a approaches 1 from the right. The reason we're approaching from the right is that if I'm going from 1 to 3, I'm going from 1 to the right to 3. Integral a to 3 dx over x minus 1 to the 2/3. Okay, now we need to find the antiderivative for these. So if you want to do a u substitution, of course you could do that. But this is really to the negative 2/3 power. So we would raise that up to positive 1/3, which means we're dividing by 1/3 or multiplying by 3. So this is going to have the limit b approaching 1 from the left. This has antiderivative of multiplying by 3, and then it's going to be x minus 1 to the positive 1/3, evaluated from 0 to b. Plus over here, same thing, limit as a approaches 1 from the right of same antiderivative. This going from a to 3. All right, let's plug the limits in, and then the integral limits, and then we'll worry about the actual limits. So this will be the limit as b approaches 1 from the left of, if I plug b in, I get 3 times b minus 1 to the 1/3, minus, if I plug 0 into this, I get negative 1 to the 1/3, which is still just negative 1, times 3, so plus 3. Okay, that plus, same thing over here. The limit as a approaches 1 from the right. If I plug 3 in, 3 minus 1 is 2 to the 1/3. I'm just going to leave that as 2 to the 1/3. Not really much you can do to that. Minus plugging a in. Okay, now let's worry about the limits. So, one little trick to limits is that if you can just plug in the number, then just plug in the number. So that's what we're going to do here. If I plug 1 in for the b, I get 1 minus 1, which is 0. 0 to the 1/3, still just 0. Over here, if I plug a to be 1 in, I get 1 minus 1 is 0 to the 1/3, still 0. So for here, I'm just going to get that constant 3. Plus, here, I'm going to get that constant 3, 2 to the 1/3 power. And that's it. That is a number, and because it is a number, that means that my integral converges. And it converges to this. Just to kind of show you what's going on for the graph, let's look at our calculator here. So here we were looking at the graph 1 over x minus 1 to the 2/3. Okay. And we'll zoom standard it just in case we weren't before. All right, so here's our graph. Remember that we have a vertical asymptote at 1, so you should see it coming up there. There it goes. I know it kind of stops here, but this really does go up to positive infinity. This is just the calculator freaking out a little bit. You can even see it has an error there at 1 on the table. Okay, so if we integrate this from 1, what was it, 1? No, it was from 0, sorry, from 0 to 3. It does cross over this integral, but this integral, the function itself approaches the asymptote so quickly that you can pretty much just say that it stops about there, like the calculator says it does, and we do have this finite integral. Okay, so those are the two different types of improper integrals: when you have infinities for the limits, or when you have an asymptote somewhere in your interval itself. And that is it for section 8.